Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world you're listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the invisible dimensions that surround us, the hidden architecture of reality that science reveals through mathematics and careful observation. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. Reality extends far beyond what human senses can perceive, unfolding across dimensions that remain forever hidden from direct observation. The universe constructs itself through geometries that consciousness can touch only through the language of mathematics, revealing precise structures that govern every interaction between matter and energy. Space itself possesses more dimensions than the familiar three of length, width, and height that define everyday experience. String theory suggests that 6 or 7 additional dimensions curl upon themselves at every point in space, compressed so tightly that they exist at scales smaller than atomic nuclei, smaller than protons, smaller than quarks, smaller than anything that light can illuminate or instruments can measure. These hidden dimensions vibrate like cosmic strings stretched across scales that dwarf human comprehension, their resonant frequencies determining the fundamental properties of every particle that exists in the observable universe. An electron's mass emerges from these vibrations, its precise value encoded in the geometry of spaces too small to imagine. A photon's energy springs from their oscillations, wavelengths and frequencies arising from dimensional harmonics that play across 11-dimensional space. The strength of gravity itself flows from the way these invisible dimensions fold and twist, creating field configurations that determine how matter attracts matter across cosmic distances. The mathematics works with elegant precision, describing particle interactions and field equations that match experimental results to extraordinary accuracy, predicting the behavior of matter and energy with decimal places extending far beyond the precision of any measuring instrument humanity has constructed. Physicists can calculate the magnetic moment of an electron to 15 decimal places, a precision equivalent to measuring the distance from New York to Los Angeles to within the width of a human hair. Such accuracy emerges from theoretical frameworks built upon the assumption of these invisible dimensions, mathematical structures that somehow capture the deepest truths about reality's hidden architecture. Yet no human eye will ever glimpse these curled dimensions directly. They exist at the Planck length, some 10 to 35 meters a scale, so impossibly small that to compare it to a proton would be like comparing a proton to the entire observable universe, a ratio so extreme that numbers begin to lose their intuitive meaning. Only took 11 dimensions to contain all of physics. Apparently, light itself cannot probe such distances because photons are far too large, like trying to explore the detailed structure of a spider's web using ocean waves that dwarf continents. At this scale, the very concepts of distance and measurement begin to lose their familiar meaning, dissolving into quantum uncertainty and mathematical abstraction, where space and time themselves become approximate concepts. These dimensions hide within every cubic centimeter of seemingly empty space, curled so tightly that even the most powerful particle accelerators cannot reveal their presence through direct collision experiments. The Large Hadron Collider, Humanity's most ambitious attempt to probe the fundamental structure of matter operates at energy scales millions of times too weak to unfurl these hidden spaces, like examining a garden hose from an airplane flying at cruising altitude, where only length appears visible while width and depth disappear into apparent one-dimensionality. These cosmic dimensions remain invisible to all direct observation, accessible only through their indirect effects on particle masses and force strengths. They exist in a realm where the classical physics of Newton gives way entirely to quantum mechanics, where particles tunnel through energy barriers that should be absolutely impenetrable, where virtual particles pop into existence and vanish again in time frames so brief that uncertainty principles render their properties fundamentally unknowable. Here, effects can precede causes in ways that challenge every intuition about temporal sequence and causation, where the act of observation itself changes the nature of reality being observed. The shape of these hidden dimensions determines which particles can exist and which forces can operate throughout the universe. If they were configured even slightly differently, electrons might not bind to protons in stable atoms, stars might not ignite nuclear fusion in their cores, chemistry might not function with sufficient complexity to build organic molecules, and the intricate structures that allow for galaxies, planets, and eventually consciousness itself might never emerge from primordial hydrogen and helium. Reality balances on the precise geometry of spaces too small to imagine, dimensions that vibrate with frequencies beyond human hearing, beyond human sight, beyond the reach of any sense that evolution has provided for navigating the macroscopic world. Scientists wonder whether these dimensions remain truly curled everywhere throughout space, or whether they might unfurl in regions of extreme gravity near black holes, where space-time itself stretches and warps under gravitational forces millions of times stronger than Earth's pull. Perhaps the event horizons of black holes provide glimpses into regions where hidden dimensions partially expand, revealing aspects of 11-dimensional geometry that remain forever concealed in ordinary space-time. During the universe's first moments, when all matter and energy compressed into volumes smaller than atomic nuclei at temperatures exceeding billions of degrees, these dimensions might have expanded briefly before settling into their current hidden configuration as the cosmos cooled and inflated. The cosmic microwave background radiation that fills all space might carry subtle imprints of their ancient dance, traces of dimensional structures that existed when the universe was less than a second old and physics operated under conditions that no earthly laboratory can reproduce. These faint signals, stretched across 13 billion years of cosmic expansion, might preserve information about dimensional geometries that determine the fundamental parameters of reality during its first fleeting moments of existence. Mathematical models suggest these dimensions vibrate constantly, their oscillations creating resonances that propagate through quantum fields, influencing the formation of particles across cosmic distances measured in billions of light years. The fundamental constants of nature, the speed of light, the electric charge of an electron, the strength of nuclear forces, the cosmological constant that drives universal expansion, all emerge from the geometry of spaces that exist everywhere, yet remain forever beyond direct experience. Like a vast musical instrument with strings tuned to frequencies that consciousness cannot hear, reality plays its symphony across dimensions that mathematics reveals, but human senses cannot touch. Even the vacuum of space, seeming empty to casual observation, thrums with the vibrations of these hidden dimensions. They curve and fold through every point where matter exists, every region where energy flows, every location where forces operate between particles, the coffee cup resting on a table, the air flowing through lungs, the photons streaming from distant stars, the gravitational waves rippling from colliding black holes, all exist embedded within these invisible geometries, their properties determined by dimensional shapes too small to detect with any conceivable instrument. Modern physics suggests that gravity itself might leak between these dimensions, spreading its influence across all 11 dimensions, while electromagnetic, weak nuclear, and strong nuclear forces remain confined to the familiar 3 spatial dimensions plus time. This dimensional bleeding might account for the mysterious weakness of gravity compared to other fundamental forces, explaining why it takes the entire mass of Earth to hold a single paper clip against the electromagnetic forces generated by a small refrigerator magnet. Gravity's apparent weakness might result from its dilution across dimensions that other forces cannot access. Reality rests upon an invisible scaffolding that consciousness can approach only through equations and mathematical abstractions, forever separated from direct experience by the fundamental limitations of scale and the boundaries of human perception. These dimensions exist not in some distant realm, but here, now, woven into the fabric of every moment, every breath, every heartbeat, every thought. They form the hidden foundation upon which all visible reality constructs itself. The invisible architecture that makes possible stars and planets, chemistry and biology. The emergence of minds capable of contemplating their own mysterious origins within spaces too small to see, too fundamental to avoid, too essential to reality to exist anywhere except everywhere at once. The vacuum of space appears empty to human perception, yet it vibrates constantly with quantum fields that permeate every cubic centimeter of the universe. These invisible fields exist even in regions devoid of matter, stretching across cosmic voids between galaxies where no atoms drift for millions of light years. Quantum field theory reveals that what seems like absolute nothingness actually seethes with activity at scales too small and too brief for any instrument to detect directly. Virtual particles materialize from pure vacuum, exist for impossibly short intervals, then vanish back into nothingness, their fleeting presence nonetheless measurable through subtle effects on nearby matter. The electromagnetic field fills all space, even where no photons travel and no electric charges exist. It fluctuates constantly at the quantum level, creating momentary photons that appear and disappear faster than light can travel the width of a proton. These vacuum fluctuations contribute measurable energy to the universe, a phenomenon so counterintuitive that physicists initially dismissed it as mathematical error. Only took 50 years to realize that empty space carries infinite energy density. They discovered. The Casimir effect demonstrates this experimentally. 2 metal plates placed extremely close together in perfect vacuum experience, attractive forces generated by quantum field oscillations in the narrow gap between them. Electron fields permeate every location where electrons might possibly exist, which encompasses all of space throughout the observable universe. These fields do not simply describe the probability of finding electrons at various locations, they constitute the fundamental reality from which electron particles emerge as localized excitations, like waves, arising on an otherwise calm ocean surface. When an electron appears to tunnel through energy barriers that classical physics deems impenetrable, it actually represents the electron field configuration shifting from one spatial region to another through quantum superposition states. The Higgs field maintains constant presence throughout space, giving mass to fundamental particles through their interactions with this invisible medium, Unlike other quantum fields that can fluctuate around zero values, the Higgs field possesses a non-zero vacuum expectation value everywhere, creating a cosmic background against which all particles acquire their characteristic masses. This field broke the original symmetry of the universe during its first fraction of a second, when temperatures dropped sufficiently for the Higgs mechanism to activate and distinguish between particles that had been identical under primordial conditions. Neutrino fields fill the universe with nearly massless particles that interact so weakly with ordinary matter that trillions pass through human bodies every second without leaving detectable traces. These fields carry information from the cores of stars, from supernovae explosions, from the cosmic microwave background, from nuclear reactors and particle accelerators, creating an invisible information network that connects every location in space to every other location through weakly interacting field excitations that travel at nearly the speed of light. Scientists wonder whether additional fields exist beyond those discovered by current experiments. Dark matter might represent excitations of fields that interact only gravitationally with ordinary matter, creating particle types that remain invisible to electromagnetic observation, yet outweigh visible matter by ratios of 5:1 throughout cosmic structures. Dark energy fields might drive the accelerating expansion of space itself, though their nature remains completely mysterious despite comprising 70% of the universe's total energy density. The quantum vacuum state represents the lowest possible energy configuration of all fields simultaneously, yet this ground state still contains residual energy from quantum fluctuations that cannot be eliminated even at absolute zero temperature. This zero-point energy contributes to the cosmological constant problem. Theoretical calculations suggest vacuum energy density should be so enormous that space itself would collapse immediately, yet observations show space expanding at an accelerating rate under the influence of dark energy, whose origin remains unknown. Field configurations can become entangled across arbitrary distances, creating correlations between widely separated regions that persist instantaneously, regardless of the spatial separation involved. When quantum fields undergo measurement at one location, their properties at distant locations change immediately, without any information traveling between the regions at light speed. This quantum entanglement violates classical intuitions about locality and causation, suggesting that space itself might not represent the fundamental arena within which physics operates. Virtual particle pairs spontaneously arise from field fluctuations, briefly borrowing energy from the quantum vacuum before annihilating back into nothingness. These virtual particles contribute to the properties of real particles through loop corrections in quantum field theory calculations, affecting electron magnetic moments, atomic energy levels, and the strength of fundamental forces. The precision of these quantum electrodynamics calculations matches experimental measurements to extraordinary accuracy, confirming that virtual particle effects represent genuine physical phenomena rather than mathematical artifacts. Field theory suggests that particles do not actually move through space in classical trajectories, but rather represent wave-like excitations propagating through quantum fields that extend throughout all regions of space-time. An electron traveling from one location to another does not follow a single path, but simultaneously explores all possible paths through quantum superposition, with the observed trajectory representing the interference pattern of probability amplitudes across infinite possible routes through the underlying electron field configuration. Temperature represents the average energy of field excitations in any given volume of space. Even at absolute zero, quantum fields continue oscillating due to Heisenberg uncertainty relations that prevent simultaneous precise knowledge of field values and their rates of change. These quantum fluctuations create an irreducible minimum activity level that persists throughout the universe, regardless of temperature, ensuring that perfect stillness cannot exist even in the deepest cosmic voids where matter density approaches zero. Symmetry breaking occurs when quantum fields adopt non-zero vacuum expectation values that favor particular directions or configurations in abstract mathematical spaces. The Higgs field-breaking electroweak symmetry represents one example, but cosmologists speculate that additional symmetry-breaking events during cosmic inflation might have determined the fundamental parameters of particle physics and the large-scale structure of space itself. These field configurations, established during the universe's first moments, continue influencing physical laws throughout cosmic history. The vacuum state itself might be metastable, existing in a local energy minimum rather than the absolute lowest possible energy configuration. If so, quantum tunneling could eventually transition the entire universe to a lower energy vacuum state, fundamentally altering the laws of physics and potentially destroying all existing structures in an expanding bubble of new physics traveling at light speed. Only took 14 billion years to maybe find out whether reality rests on stable ground. Apparently, such speculation remains beyond experimental verification, yet the mathematical consistency of quantum field theory permits these possibilities within current theoretical frameworks. Fields interact with each other through coupling terms in the fundamental equations, creating complex dynamics where changes in one field influence configurations in others across vast distances and timescales. These field interactions generated the particles and forces that shaped cosmic evolution. From the first moments after the Big Bang through stellar nucleosynthesis, galaxy formation, planetary development, and the emergence of biological complexity from quantum mechanical foundations that operate continuously in every location throughout the observable universe, space-time curves and bends under the influence of mass and energy, creating invisible topographical features that guide the motion of everything from photons to galaxies. Einstein's general relativity reveals that what humans perceive as gravitational force actually represents the tendency of objects to follow the straightest possible paths through curved four-dimensional space-time. Matter tells space-time how to curve, and curved space-time tells matter how to move, creating a dynamic feedback loop that governs cosmic architecture from planetary orbits to the expansion of the universe itself. The curvature exists everywhere, though its intensity varies dramatically across different regions of space. Near Earth's surface, space-time curves so gently that classical physics provides excellent approximations for most purposes. Yet precise measurements reveal that time flows slightly faster at higher altitudes where gravitational fields weaken. GPS satellites must account for these relativistic effects continuously, adjusting their clocks to compensate for time dilation caused by Earth's gravitational field. Only took a century after Einstein to make relativity essential for navigation technology. Apparently, massive objects create space-time depressions like bowling balls placed on stretched rubber sheets. Though this analogy fails to capture the four-dimensional nature of actual gravitational curvature, the Sun warps space-time in its vicinity, causing Earth to orbit not because of attractive forces but because our planet follows geodesic paths through curved geometry. Light from distant stars bends as it passes near the Sun during solar eclipses, following the curved space-time architecture that massive objects impose on their surroundings through pure geometry rather than mechanical interaction. black holes represent regions where space-time curvature becomes so extreme that even light cannot escape once it crosses the event horizon boundary. At the center of each black hole, general relativity predicts a singularity where curvature becomes infinite and the known laws of physics break down completely. These cosmic laboratories provide natural experiments in extreme gravitational physics, revealing how space-time behaves under conditions that no earthly laboratory could ever reproduce through artificial means. The curvature of space-time propagates outward from accelerating masses as gravitational waves, ripples in the fabric of reality itself that travel at the speed of light. When two black holes spiral together before merging, they create space-time distortions so violent that the resulting gravitational waves can be detected by laser interferometers on Earth, despite traveling billions of light years. These waves carry information about cosmic events encoded directly in the geometry of space and time, providing a new observational window into the universe's most energetic phenomena. Scientists measure space-time curvature through its effects on the behavior of matter, energy, and light. Yet the curvature itself remains invisible to direct observation. Geodetic surveys can detect minute changes in Earth's gravitational field caused by underground mass distributions, revealing subsurface geological structures through their subtle influence on local space-time geometry. Ocean currents, atmospheric circulation patterns, and even groundwater flow create measurable perturbations in gravitational fields that reflect the dynamic redistribution of mass across Earth's surface. The expansion of the universe represents a stretching of space-time itself rather than galaxies moving through pre-existing space. Distant galaxies recede from Earth not because they travel away through space, but because new space-time continuously comes into existence between them, increasing cosmic distances without violating speed-of-light limitations. This expansion affects the wavelengths of light traveling across cosmic distances, shifting electromagnetic radiation toward longer wavelengths in proportion to the distance traveled through expanding space-time. Cosmic inflation theory suggests that space-time itself underwent exponential expansion during the universe's first fraction of a second, stretching quantum fluctuations to cosmic scales that seeded the formation of galaxies and large-scale structure. This inflationary expansion would have occurred far faster than light speed, but no information traveled faster than light because space itself expanded rather than objects moving through space. The cosmic microwave background radiation preserves imprints of these primordial space-time fluctuations, providing observational evidence for inflation's effects on cosmic geometry. Time dilation occurs wherever space-time curvature exists, causing clocks to run at different rates, depending on their gravitational environment and velocity through space. Astronauts returning from the International Space Station have aged slightly less than people on Earth's surface due to both special relativistic effects from orbital velocity and general relativistic effects from reduced gravitational field strength at higher altitudes. These time dilation effects accumulate continuously throughout cosmic history, creating temporal gradients across different regions of space. The geometry of space-time itself might possess intrinsic curvature, even in regions devoid of matter and energy. Dark energy appears to cause space-time to expand at an accelerating rate throughout cosmic history, suggesting that empty space possesses non-zero energy density that creates repulsive gravitational effects. This vacuum energy density remains constant as space expands, implying that new dark energy continuously comes into existence as space-time itself increases in volume through cosmic expansion. Scientists wonder whether space-time represents a fundamental aspect of reality or an emergent property arising from more basic quantum mechanical processes. Some theoretical approaches suggest that space and time might crystallize from quantum entanglement networks at microscopic scales, with smooth space-time geometry emerging as a statistical average over quantum fluctuations in underlying degrees of freedom that operate below the Planck scale, where general relativity and quantum mechanics both break down. Wormholes represent hypothetical tunnels through space-time that could connect distant regions of the universe through shortcuts that bypass normal three-dimensional space. While mathematically consistent with general relativity, such space-time configurations would require exotic matter with negative energy density to remain stable against collapse. These speculative structures illustrate how space-time curvature could potentially create topological features more complex than the smooth manifolds typically assumed in cosmological models. The equivalence principle states that gravitational acceleration cannot be distinguished from acceleration through flat space-time, revealing the deep connection between geometry and physics that underlies general relativity. Someone falling freely in Earth's gravitational field experiences weightlessness, identical to floating in empty space far from any massive objects, demonstrating that gravity represents space-time curvature rather than a conventional force. This principle suggests that the distinction between geometry and physics might be arbitrary, with gravitational phenomena representing pure geometry rather than mechanical interactions. Frame dragging occurs when rotating massive objects twist the space-time around them, causing nearby objects to experience additional accelerations beyond those predicted by Newtonian gravity. Earth's rotation creates measurable frame dragging effects that influence the orbits of satellites, while rapidly spinning neutron stars and black holes generate extreme space-time twisting that affects the behavior of matter in their vicinity. These effects demonstrate that space-time possesses dynamic properties that respond to both the distribution and motion of matter and energy throughout the universe. Space-time curvature operates continuously at every location throughout the cosmos, creating an invisible landscape of gravitational hills and valleys that determines the trajectories of everything from subatomic particles to galactic superclusters. This curved four-dimensional architecture remains completely imperceptible to human senses, yet governs every aspect of cosmic evolution, from the formation of the first stars to the eventual fate of the universe itself, written in mathematical relationships that describe reality's deepest geometric foundations. Dark matter permeates the universe in quantities that dwarf all visible matter by ratios exceeding 5:1. Yet it interacts with ordinary matter only through gravitational forces that remain undetectable except through their cumulative effects on cosmic structures. This invisible substance forms the scaffolding upon which galaxies construct themselves, creating gravitational wells that capture and organize ordinary matter into the luminous structures that telescopes can observe. Without dark matter's gravitational influence, galaxies would lack sufficient mass to hold themselves together, and the cosmic web of galactic clusters and superclusters could never have formed from the smooth distribution of matter that existed shortly after the Big Bang. Galaxy rotation curves provide the most compelling evidence for dark matter's existence, revealing that stars in galactic outskirts orbit far too rapidly to remain gravitationally bound by the visible matter alone. According to Newtonian mechanics, orbital velocities should decrease with distance from galactic centers as the gravitational influence of central mass concentrations weakens. Yet observations show that rotation speeds remain nearly constant across entire galactic disks. This discrepancy requires additional invisible mass distributed throughout galactic halos, extending far beyond the regions where stars and gas create observable light. Gravitational lensing reveals dark matter's presence through its effects on light from distant galaxies. bending and distorting background images in patterns that map the distribution of invisible mass concentrations. The bullet cluster provides particularly dramatic evidence, showing how dark matter and ordinary matter behave differently during a high-velocity collision between galactic clusters. While ordinary matter interacted electromagnetically and slowed during the collision, dark matter passed through, largely unaffected, separating spatially from the visible gas and creating gravitational lensing signatures displaced from the observable matter concentrations. Computer simulations of cosmic structure formation require dark matter to reproduce the observed distribution of galaxies across cosmic scales. These N-body simulations model the gravitational interactions of millions of dark matter particles over billions of years of cosmic evolution, successfully predicting the formation of galactic filaments, clusters, and voids that match observational surveys. Only took 70 years to realize that most of the universe remains invisible, apparently. Without dark matter's gravitational influence, ordinary matter would have remained too smoothly distributed to form the complex hierarchical structures that characterize the modern cosmos. The nature of dark matter particles remains completely unknown, despite decades of increasingly sophisticated detection experiments. Leading candidates include weakly interacting massive particles that were produced in enormous quantities during the early universe but interact with ordinary matter only through gravity and possibly the weak nuclear force. These hypothetical particles would pass through Earth continuously without leaving detectable traces in conventional matter, requiring specialized detectors buried deep underground to shield against cosmic ray backgrounds that could mask subtle dark matter interaction signals. Dark matter's gravitational effects operate on scales ranging from individual galaxies to the largest cosmic structures observable throughout the universe. Galactic clusters contain dark matter concentrations that can be mapped through gravitational lensing, revealing complex substructure that reflects the merger history of constituent galaxy groups over cosmic time. The cosmic web itself represents dark matter's large-scale distribution, with galaxies forming like decorations strung along invisible filaments that span hundreds of millions of light-years between massive node concentrations. Scientists wonder whether dark matter consists of a single particle type or multiple species with different masses and interaction strengths. Some theoretical models suggest that dark matter might form its own complex physics sector with dark photons, dark nuclei, and dark chemistry that operates parallel to ordinary matter but remains invisible to electromagnetic observation. Such dark sectors could potentially explain observed small-scale discrepancies between dark matter simulations and galactic observations that suggest more complex behavior than simple gravitational interactions alone. Alternative theories propose that dark matter phenomena might result from modifications to gravitational physics rather than invisible matter particles. Modified Newtonian dynamics and other approaches attempt to explain galactic rotation curves and gravitational lensing through changes to gravity's behavior on large scales, or in weak gravitational fields. However, these alternatives struggle to simultaneously explain all dark matter observations, particularly the bullet cluster evidence that shows gravitational effects separated from visible matter concentrations. The cosmic microwave background radiation carries imprints of dark matter's influence during the universe's first 380,000 years, when ordinary matter remained ionized and coupled to photons through electromagnetic interactions. Dark matter decoupled from radiation much earlier and began forming gravitational potential wells that influenced the acoustic oscillations preserved in the microwave background. These observations provide independent confirmation of dark matter's existence and constrain its properties during the universe's earliest observable epochs. Dark matter halos surround every galaxy and extend far beyond the visible stellar distributions, creating invisible reservoirs of gravitational potential that influence galactic evolution over cosmic time. These halos likely formed before the galaxies themselves, providing gravitational scaffolding that enabled ordinary matter to cool and condense into stars and planetary systems. The Milky Way's dark matter halo contains hundreds of times more mass than all its visible stars combined. Yet this vast invisible structure remains completely imperceptible, except through its gravitational influence on stellar motions. Tidal streams of stars stripped from dwarf galaxies reveal the gravitational influence of dark matter substructure within the Milky Way's halo, creating observable signatures of invisible mass concentrations that would otherwise remain undetectable. These stellar streams act as sensitive probes of dark matter distribution, their shapes and motions encoding information about encounters with dark matter, subhalos, that perturb their orbits through purely gravitational interactions over millions of years. The abundance of dark matter throughout cosmic history affects the formation rate of stars, galaxies, and larger structures by determining how efficiently ordinary matter can cool and condense within gravitational potential wells. Too little dark matter would prevent galaxy formation, while too much would cause structures to collapse so rapidly that stars could not form before being disrupted by gravitational instabilities. The observed dark matter density appears finely tuned to permit the complex cosmic evolution that led to planets, life, and consciousness within a universe dominated by invisible matter. Direct detection experiments continue searching for dark matter particle interactions with ordinary matter, using increasingly sensitive detectors that monitor for nuclear recoil events caused by dark matter particles scattering off atomic nuclei. These experiments must distinguish genuine dark matter signals from radioactive backgrounds, cosmic ray interactions, and environmental contamination that could mimic the extremely rare interaction events predicted by theoretical models. The absence of confirmed detections despite improving sensitivity suggests that dark matter interactions with ordinary matter are even weaker than initially predicted. Dark matter's gravitational influence extends beyond galactic scales to affect cosmic expansion and the formation of the largest structures in the universe, creating an invisible cosmic web that channels matter and energy along filamentary pathways connecting galactic clusters across billions of light years. This hidden architecture determines where galaxies form, how they evolve, and ultimately the distribution of all visible matter throughout space, making dark matter the primary sculptor of cosmic structure, despite its complete invisibility to all electromagnetic observation methods, yet devised by human ingenuity and technological advancement. The electromagnetic spectrum extends far beyond the narrow range of wavelengths that human vision can perceive, revealing cosmic phenomena invisible to the naked eye across frequencies spanning more than 20 orders of magnitude. Radio waves stretch across wavelengths measured in meters and kilometers, carrying signals from pulsars, quasars, and the remnant radiation from the Big Bang itself. These long-wavelength photons penetrate cosmic dust clouds that block visible light, allowing astronomers to observe star formation regions and galactic centers that remain hidden from optical telescopes. The universe speaks in radio frequencies that require vast antenna arrays to decode messages transmitted across billions of light years. Microwaves fill all space with the cosmic microwave background radiation, the afterglow of the universe's hot, dense beginning, now cooled by cosmic expansion to a temperature just 2.7 degrees above absolute zero. This invisible radiation preserves imprints of quantum fluctuations that existed when the universe was smaller than a grapefruit, stretched to cosmic scales by inflationary expansion, and later amplified by gravity into the seeds that grew into galaxies and galactic clusters. Only took 380,000 years for the universe to cool enough for photons to travel freely, creating this fossil light that telescopes can detect in every direction across the sky. Infrared radiation reveals heat signatures from objects too cool to emit visible light, unveiling star formation nurseries shrouded in dust, brown dwarf stars that never achieved nuclear fusion, and the thermal emission from planets orbiting distant stars. The James Webb Space Telescope observes in infrared wavelengths to penetrate cosmic dust and see the first galaxies that formed when the universe was less than 1 billion years old. These ancient structures appear highly redshifted due to cosmic expansion. Their visible light stretched into infrared frequencies during the journey across space and time to reach modern detectors. Ultraviolet photons carry enough energy to ionize atoms and break molecular bonds, creating conditions that sterilize planetary surfaces while simultaneously driving the chemistry that forms complex organic molecules in interstellar space. Hot, massive stars emit most of their energy at ultraviolet wavelengths invisible to human eyes but detectable by space-based telescopes above Earth's protective atmosphere. These energetic photons heated the intergalactic medium during cosmic reionization, when the first stars and galaxies ionized hydrogen throughout the universe, approximately 1 billion years after the Big Bang. X-rays emerge from some of the most extreme environments in the cosmos, generated by matter falling into black holes, neutron star surfaces with magnetic fields trillions of times stronger than Earth's, and shock waves from supernova explosions that accelerate particles to near light speed. X-ray telescopes reveal accretion disks around black holes, where matter reaches temperatures of millions of degrees before crossing event horizons, creating brilliant emission that outshines entire galaxies despite originating from regions smaller than planetary orbits. Gamma rays represent the highest energy electromagnetic radiation, produced by radioactive decay, matter-antimatter annihilation, and cosmic ray interactions with interstellar gas. Gamma-ray bursts release more energy in seconds than the Sun will emit during its entire 10 billion-year lifetime, creating brief flashes of gamma radiation visible across cosmic distances exceeding 10 billion light-years. These catastrophic events likely result from hypernova explosions or neutron star mergers that create conditions so extreme they briefly outshine observable portions of the universe. The atmosphere blocks most electromagnetic radiation outside the visible spectrum, requiring space-based observatories to study celestial phenomena at wavelengths absorbed by atmospheric gases. Earth's magnetic field deflects charged particles from reaching the surface, but electromagnetic radiation travels unimpeded through space until encountering atmospheric molecules that selectively absorb photons based on their energies. This atmospheric filtering protected the evolution of life on Earth's surface, while simultaneously limiting ground-based astronomy to narrow wavelength windows. Radio astronomy reveals pulsars spinning hundreds of times per second, their lighthouse beams of radio emission sweeping across space with clockwork precision that rivals atomic time standards. These rapidly rotating neutron stars concentrate the mass of the Sun into spheres only 20 kilometers in diameter, creating gravitational fields so intense that matter on their surfaces weighs billions of times more than on Earth. The radio pulses arrive with such regularity that astronomers initially considered whether they might represent signals from extraterrestrial civilizations. Infrared surveys map the warm dust lanes threading through spiral galaxies, revealing star formation activity hidden from optical observation by intervening cosmic dust. This dust absorbs starlight at visible wavelengths and re-emits the energy as thermal infrared radiation, creating heat signatures that trace ongoing stellar birth in molecular cloud complexes. The Spitzer Space Telescope and other infrared observatories discovered that star formation rates throughout cosmic history were higher than visible light observation suggested, with much stellar activity obscured by dust. Scientists wonder whether undiscovered forms of electromagnetic radiation might exist beyond the known spectrum, though quantum mechanics suggests that photons with arbitrarily high or low energies should behave according to established physical principles. The highest energy gamma rays detected by ground-based air shower arrays approach energies where quantum gravity effects might become important, potentially revealing new physics at energy scales that particle accelerators cannot reach through terrestrial experiments. Synchrotron radiation emerges when charged particles spiral through magnetic fields at relativistic speeds, creating polarized emission across broad ranges of electromagnetic frequencies, supernova remnants, active galactic nuclei, and Jupiter's radiation belts all generate synchrotron emission that reveals magnetic field structures and particle acceleration mechanisms operating throughout the universe. This radiation provides diagnostic information about cosmic magnetic fields that would otherwise remain completely undetectable. The cosmic microwave background exhibits tiny temperature fluctuations that encode information about the universe's geometry, composition, and evolution during its first few 100,000 years. These fluctuations span angular scales from degrees to arc minutes across the sky, preserving acoustic oscillations that propagated through the hot plasma filling space before atoms formed and photons began traveling freely. The precise pattern of these temperature variations confirms theoretical predictions about cosmic inflation, dark matter, and dark energy with extraordinary accuracy. Telescopes operating across multiple wavelengths reveal different aspects of the same cosmic phenomena, like examining a sculpture under different lighting conditions to understand its three-dimensional structure. Galaxies appear dramatically different when observed in radio waves, infrared, visible light, ultraviolet, X-rays, and gamma rays, each wavelength range highlighting different physical processes and structural components. Multi-wavelength astronomy creates comprehensive pictures of cosmic objects by combining observations across the electromagnetic spectrum. The search for extraterrestrial intelligence monitors radio frequencies where hypothetical alien civilizations might transmit intentional signals across interstellar distances. Radio waves travel through interstellar space with minimal absorption or scattering, making them ideal for long-distance communication between technologically advanced species. The waterhole between hydrogen and hydroxyl spectral lines represents a naturally quiet region of the radio spectrum where artificial signals might be most easily detected above natural cosmic background noise. Electromagnetic radiation carries information across the universe at light speed, creating an information network that connects every location in space to every other location through photons that preserve details about their sources across cosmic distances and timescales. The light reaching Earth tonight from distant galaxies carries messages about cosmic conditions that existed billions of years ago, providing observational access to the universe's history encoded in electromagnetic signals traveling through space since shortly after the Big Bang itself occurred. Quantum entanglement creates instantaneous correlations between particles separated by arbitrary distances throughout the universe, establishing connections that persist regardless of the spatial separation involved. and appear to violate classical intuitions about locality and information transfer. When two particles become entangled through direct interaction or common origin, measuring the quantum state of one particle immediately determines the corresponding state of its entangled partner, even if that partner exists on the opposite side of the galaxy. This phenomenon occurs without any signal traveling between the particles at light speed, suggesting that quantum mechanics operates through non-local connections that transcend the familiar constraints of space and time. Einstein famously described entanglement as spooky action at a distance, because it seemed to contradict special relativity's prohibition against faster-than-light information transfer. However, careful analysis reveals that while entangled particles exhibit correlated properties instantaneously across arbitrary distances, no useful information can be transmitted between distant observers through entanglement alone. The correlations emerge only when measurement results are compared, requiring classical communication channels that respect light speed limitations. Only took 50 years to prove that quantum mechanics really is non-local. Apparently, Bell's theorem demonstrates that no physical theory based on local realism can reproduce all the predictions of quantum mechanics, forcing physicists to abandon either locality or realism in their fundamental description of nature. Experimental tests of Bell inequalities consistently confirm quantum mechanical predictions while violating the constraints that local, realistic theories must satisfy. These experiments use photon pairs created through spontaneous parametric down-conversion, where a single high-energy photon splits into two lower-energy photons with entangled polarization states that remain correlated despite traveling to different detector locations. The EPR paradox illustrates the conceptual difficulties that entanglement creates for classical understanding of physical reality. If quantum mechanics provides complete descriptions of physical systems, then measuring one member of an entangled pair instantly affects its distant partner's properties, apparently allowing action at a distance. Alternatively, if particles possess definite properties independent of measurement, then quantum mechanics provides incomplete descriptions of reality. Modern experiments consistently support quantum mechanics while ruling out local hidden variable theories that would restore classical realism. Quantum entanglement enables technologies like quantum cryptography, which uses entangled photon pairs to detect eavesdropping attempts on secure communication channels. Any attempt to intercept entangled photons necessarily disturbs their quantum states, revealing the presence of unauthorized monitoring to legitimate users. Quantum key distribution protocols exploit this fundamental property of quantum measurement to establish provably secure communication links, with security guaranteed by the laws of physics rather than computational complexity assumptions. Scientists wonder whether entanglement might play essential roles in biological processes, potentially explaining the remarkable efficiency of photosynthesis in converting sunlight to chemical energy. Some theoretical models suggest that quantum coherence and entanglement help energy transfer through photosynthetic complexes by allowing excitation energy to simultaneously explore multiple pathways and select optimal routes through quantum interference effects. These quantum biological phenomena would require maintaining delicate quantum states in warm, noisy biological environments, where decoherence typically destroys quantum effects rapidly. Many worlds' interpretation suggests that entanglement correlations reflect the branching of reality into parallel universes, where different measurement outcomes occur simultaneously. Under this view, measuring an entangled particle splits the observer into multiple versions existing in different universal branches, with each version seeing results consistent with quantum mechanical predictions. The apparent randomness of individual quantum measurements emerges from the observer's inability to perceive other branches where different outcomes occurred. Entanglement swapping allows quantum correlations to be transferred between particles that never directly interacted, creating extended networks of quantum connections across multiple particle systems. Bell state measurements on intermediate particles can entangle distant particles that originated from separate sources, enabling the construction of quantum networks spanning arbitrary distances. These protocols form the foundation for proposed quantum Internet architectures that would enable distributed quantum computing and unconditionally secure global communications. The decoherence process gradually destroys entanglement through interactions with environmental systems that cannot be controlled or monitored precisely. Photons traveling through space experience decoherence due to interactions with cosmic microwave background radiation, solar wind particles, and interstellar dust grains that scramble quantum phase relationships. Maintaining entanglement over astronomical distances would require isolation from all environmental influences, making cosmic-scale quantum correlations extremely fragile and short-lived under realistic conditions. Quantum error correction schemes attempt to preserve entanglement against decoherence by encoding quantum information redundantly across multiple physical systems and detecting errors without directly measuring the protected quantum states. These protocols require careful balancing between error detection and the quantum no-cloning theorem, which prevents perfect copying of unknown quantum states. Successful quantum error correction would enable large-scale quantum computers that maintain coherent quantum calculations despite inevitable environmental decoherence. Entanglement entropy measures the amount of quantum correlation between different regions of space, providing insights into the structure of quantum field theory vacuum states and black hole physics. The entropy scales with the area of boundaries between regions rather than their volumes, suggesting deep connections between quantum entanglement and gravitational physics. Black hole entropy might emerge from entanglement between quantum degrees of freedom inside and outside event horizons, with Hawking radiation resulting from the gradual disentanglement of vacuum fluctuations. Experimental verification of entanglement requires statistical analysis of many measurement trials to distinguish genuine quantum correlations from classical correlations that might arise from common cause explanations. Loophole-free Bell tests use space-like separated detectors where measurement choices are made after entangled particles have separated, eliminating the possibility that hidden communication between detectors could explain the observed correlations. These experiments confirm that nature exhibits genuine non-locality at the quantum scale. Quantum teleportation uses entanglement to transfer complete quantum state information between distant locations without physically moving the particles that carry the information. The original quantum state is destroyed during teleportation, while an exact copy appears at the destination, preserving the quantum no-cloning theorem while enabling quantum state transfer. Teleportation requires both quantum entanglement and classical communication, combining non-local quantum correlations with light-speed information transfer to achieve quantum state reconstruction. Macroscopic entanglement might exist in specialized systems like superconductors, where millions of electrons form collective quantum states that maintain coherence across macroscopic distances. These systems bridge the gap between microscopic quantum effects and classical physics, demonstrating that quantum mechanics can operate on scales directly observable by human senses under appropriate conditions. Josephson junctions create macroscopic quantum superposition states where electric currents flow simultaneously in opposite directions. The measurement problem in quantum mechanics becomes particularly acute for entangled systems, where measuring one particle apparently causes instantaneous wave function collapse for its distant partner. Various interpretations attempt to resolve this conceptual difficulty through different mechanisms, from pilot wave theories with non-local hidden variables to many-world scenarios where all measurement outcomes occur in parallel realities. The persistence of this interpretational puzzle reflects deep remaining mysteries about the nature of quantum reality. Cosmic ray interactions in Earth's atmosphere create entangled particle pairs that briefly maintain quantum correlations before decoherence destroys their non-local connections, demonstrating that entanglement occurs naturally throughout the universe wherever quantum systems interact and separate. These fleeting quantum correlations connect particles across scales from subatomic to astronomical, weaving an invisible web of quantum relationships that permeate space while remaining undetectable, except through careful experimental measurement of correlation patterns that reveal the non-local foundations underlying all physical reality. The Higgs field permeates every cubic centimeter of space throughout the universe, maintaining a non-zero vacuum expectation value that gives mass to fundamental particles through their interactions with this invisible cosmic medium. Unlike other quantum fields that fluctuate around zero values in their ground states, the Higgs field settled into a stable configuration with constant background energy density when the universe cooled sufficiently during its first fraction of a second. This symmetry-breaking transition fundamentally altered the nature of reality, distinguishing between particle types that had been identical under the primordial high-energy conditions that existed immediately after the Big Bang. Before symmetry breaking occurred, all fundamental particles remained massless and travelled at light speed through space, creating a universe where electrons could not bind to atomic nuclei and stable matter could not form. The Higgs mechanism activated when cosmic temperatures dropped below approximately 1 trillion degrees, allowing the Higgs field to acquire its vacuum expectation value and begin conferring mass upon particles through their coupling strengths to this omnipresent field. Particles that interact strongly with the Higgs field acquire large masses, while those that interact weakly remain nearly massless, and photons that do not interact with the Higgs field at all remain perfectly massless and continue travelling at light speed. The discovery of the Higgs boson at the Large Hadron Collider confirmed the existence of this field through the detection of particle excitations created when protons collided at energies sufficient to disturb the Higgs field's vacuum configuration. These excitations manifest as short-lived Higgs particles that decay almost immediately into other particles, leaving characteristic signatures in detector systems designed to reconstruct the properties of particles created during high-energy collisions. Only took 50 years and the most powerful particle accelerator ever built to confirm that empty space has structure. Apparently, the Higgs field couples to particles proportionally to their masses, creating a feedback relationship where massive particles interact more strongly with the field that gives them mass in the first place. This coupling pattern explains why the top quark, the most massive known fundamental particle, interacts most strongly with the Higgs field, while neutrinos with their tiny masses interact so weakly that they barely notice the field's presence as they stream through space at nearly light speed. Scientists wonder whether the Higgs field exists in its lowest possible energy state, or whether it might occupy a metastable configuration that could eventually decay to an even lower energy level. If the current Higgs vacuum represents a local rather than global energy minimum, quantum tunneling could eventually trigger a phase transition that would fundamentally alter the laws of physics throughout a bubble expanding at light speed. Such a vacuum decay event would change particle masses and force strengths, potentially destroying all existing structures in the universe. The electroweak unification reveals how the Higgs mechanism broke the original symmetry between electromagnetic and weak nuclear forces, creating the distinct forces observed at low energies while preserving their underlying unity at high energies. Before symmetry breaking, photons and W and Z bosons remained massless and indistinguishable, mediating a single electroweak force. The Higgs field gave mass to W and Z bosons while leaving photons massless, creating the separation between electromagnetic interactions that operate over infinite range and weak nuclear interactions that remain confined to subatomic distances. Inflation theory suggests that a different scalar field, similar to the Higgs field but with different properties, drove the exponential expansion of space during the universe's first fraction of a second. This inflaton field would have possessed enormous energy density that gradually decayed into ordinary matter and radiation as cosmic expansion stretched quantum fluctuations to macroscopic scales. The transition from inflation to normal expansion might have involved phase transitions similar to electroweak symmetry breaking, but occurring at much higher energy scales. The hierarchy problem questions why the Higgs field maintains its observed vacuum expectation value, rather than receiving enormous corrections from quantum loop effects involving virtual particles at high energies. Theoretical calculations suggest that quantum corrections should drive the Higgs mass to values near the Planck scale. Yet observations show a much lighter Higgs boson. This discrepancy might indicate new physics beyond the standard model, such as supersymmetry or extra dimensions that cancel problematic quantum corrections. Grand unified theories propose that the Higgs mechanism represents one example of spontaneous symmetry, breaking that occurred multiple times during cosmic history, as the universe cooled and fundamental forces separated from their primordial unified state. Each symmetry-breaking transition would have involved scalar fields acquiring vacuum expectation values, creating the hierarchy of energy scales that characterizes particle physics from the Planck scale down to ordinary atomic energies. The cosmological constant problem relates to the Higgs field's contribution to vacuum energy density, which theoretical calculations suggest should be enormous compared to the observed dark energy that drives cosmic acceleration. The Higgs vacuum expectation value should contribute significantly to the energy density of empty space. Yet observations show that vacuum energy remains small enough to permit cosmic structure formation. This discrepancy represents one of theoretical physics' most serious fine-tuning problems. Higgs portal interactions might connect ordinary matter to dark matter through the Higgs field, providing a mechanism for dark matter particles to acquire mass while remaining invisible to electromagnetic observations. Some theoretical models propose that dark matter consists of particles that interact only gravitationally and through Higgs exchange, making them detectable only through their gravitational effects and extremely rare interactions with Higgs bosons produced in particle accelerator experiments. The weak-scale stabilization problem asks why the Higgs field settled at its observed vacuum expectation value rather than some other energy scale determined by more fundamental physics. The ratio between the Higgs vacuum expectation value and the Planck scale involves extremely small numbers that seem to require precise fine-tuning to produce a universe where atoms can form and chemistry can operate. This apparent fine-tuning motivates theoretical approaches like anthropic reasoning or multiverse scenarios. Composite Higgs models propose that the Higgs boson might not represent a fundamental particle, but rather a bound state of more basic constituents, similar to how atomic nuclei emerge from quarks and gluons. These theories attempt to explain the hierarchy problem by making the Higgs field's properties emerge from strongly interacting dynamics at higher energy scales, potentially eliminating the need for fine-tuning in fundamental parameters. The Mexican hat potential describes the mathematical structure that allows the Higgs field to acquire a non-zero vacuum expectation value through spontaneous symmetry breaking. This potential energy function possesses rotational symmetry around its maximum at zero field value, but the minimum energy configuration occurs at non-zero field values, arranged in a circle around the central maximum. The Higgs field chooses one particular direction in this circle, breaking the original symmetry while maintaining the underlying physics rotational invariance. Phase transitions in condensed matter systems provide analogies for understanding how the Higgs mechanism operates in particle physics, with phenomena like superconductivity and ferromagnetism exhibiting spontaneous symmetry breaking similar to electroweak symmetry breaking. These analogies help physicists understand how macroscopic properties can emerge from underlying symmetries, while providing experimental tests of theoretical concepts that operate at energy scales far beyond direct human experience. The Higgs field's influence extends throughout cosmic history from the first moments after the Big Bang to the present day, determining which particles can exist and how they interact through fundamental forces. This invisible medium shapes every aspect of matter's behavior while remaining completely imperceptible except through its effects on particle masses and the rare excitations detected in high-energy particle collisions, making it simultaneously the most pervasive and most hidden aspect of physical reality. Neutrinos stream through the universe in vast numbers, with trillions of these nearly massless particles passing through every square centimetre of space each second without leaving detectable traces in ordinary matter. These ghostly particles interact so weakly with atoms that they can travel through entire planets, stars, and even dense neutron star cores with only infinitesimal probabilities of collision. A neutrino could pass through a light year of solid lead with only a 50% chance of interacting with a single atomic nucleus, demonstrating the extraordinary weakness of neutrino interactions with ordinary matter that makes up familiar objects. The Sun produces neutrinos continuously through nuclear fusion reactions in its core, where hydrogen nuclei combine to form helium while releasing neutrinos that escape immediately without interacting with the solar interior. These solar neutrinos carry information directly from fusion reactions, occurring 150 million kilometers away and 700,000 kilometers beneath the Sun's visible surface, providing real-time observations of stellar nuclear processes that photons cannot deliver due to their million-year journey through the solar interior. Only took 40 years to solve the solar neutrino problem and discover that neutrinos have mass. Apparently, cosmic ray interactions with Earth's atmosphere create neutrinos when high-energy protons from space collide with atmospheric nuclei, producing cascades of secondary particles that decay into neutrinos traveling in all directions. These atmospheric neutrinos provide natural particle beams for studying neutrino properties, with some neutrinos traveling upward through Earth after being created in the atmosphere on the planet's opposite side. Neutrino detectors buried deep underground can distinguish between downward traveling neutrinos created in the atmosphere above and upward traveling neutrinos that have passed through the entire planet. Supernovae explosions release enormous numbers of neutrinos when massive stars collapse and their cores reach nuclear densities, creating conditions so extreme that even weakly interacting neutrinos are produced and trapped temporarily before escaping into space. Supernova 1987A provided the first detection of neutrinos from stellar collapse, with underground detectors recording neutrino bursts that arrived hours before visible light from the explosion reached Earth. These neutrinos carried energy equivalent to the Sun's total light output over 10 billion years. demonstrating the enormous neutrino luminosity of core collapse supernovae. The cosmic neutrino background fills all space with relic neutrinos produced during the first few seconds after the Big Bang, when the universe was hot and dense enough for thermal equilibrium between neutrinos and other particles. These primordial neutrinos decoupled from matter and radiation when cosmic temperatures dropped below 1 billion degrees, creating a uniform neutrino background with approximately 330 neutrinos per cubic centimeter throughout space. This neutrino background remains undetected due to the extremely low energies of relic neutrinos, but it carries information about cosmic conditions from earlier times than the cosmic microwave background radiation. Neutrino oscillations occur as these particles travel through space and spontaneously transform between three different types called electron, muon, and tau neutrinos. This oscillation phenomenon proves that neutrinos possess mass, though their masses remain so small that determining precise values requires extraordinarily sensitive experiments. The oscillation probabilities depend on travel distance and neutrino energy, allowing scientists to study neutrino properties using both terrestrial particle accelerator beams and natural neutrino sources like the Sun, and cosmic ray interactions. Scientists wonder whether sterile neutrinos might exist beyond the three known types, potentially contributing to dark matter or influencing cosmic structure formation through their gravitational effects. These hypothetical particles would interact even more weakly than ordinary neutrinos, making them essentially impossible to detect except through their contributions to cosmic matter density. Some experimental anomalies suggest possible evidence for sterile neutrinos, though confirming their existence would require new theoretical frameworks for understanding particle physics beyond the standard model. Neutrino astronomy opens observational windows into cosmic phenomena that remain hidden from electromagnetic observations, allowing scientists to study the cores of stars, the centers of galaxies, and the interiors of cosmic ray acceleration regions. The IceCube Neutrino Observatory uses Antarctic ice as the detection medium, monitoring for Cherenkov light produced when high-energy neutrinos occasionally interact with ice nuclei and create charged particles traveling faster than light speed in the ice medium. The Mini Boone and LSND experiments reported neutrino oscillation signatures that cannot be explained by three-neutrino mixing, suggesting possible evidence for additional neutrino types or new physics beyond current theoretical understanding. These experimental anomalies motivate continued investigations using more sensitive detectors and different experimental techniques to either confirm or refute the possibility of physics beyond the three-neutrino standard model paradigm. Reactor neutrinos produced by nuclear power plants provide controlled sources for studying neutrino properties at short distances, with experiments monitoring the flux and energy spectrum of neutrinos produced by uranium fission reactions. These experiments can detect small changes in neutrino properties over distances of kilometers, providing precision measurements of neutrino oscillation parameters that complement studies using natural neutrino sources from astrophysical objects. The atmospheric neutrino anomaly revealed that neutrinos arriving from different directions showed unexpected flux variations that could only be explained by neutrino oscillations during their travel through Earth's interior. Neutrinos created in the atmosphere directly overhead travel only tens of kilometers before reaching underground detectors, while those created on Earth's opposite side travel 12,800 kilometers through the planet's interior, providing different oscillation baselines for comparing neutrino detection rates. Neutrinoless double beta decay represents a hypothetical process that could reveal whether neutrinos are their own antiparticles, with profound implications for understanding the matter-antimatter asymmetry observed throughout the universe. This extremely rare decay process if it exists, would violate conservation of lepton number and provide insights into the fundamental nature of neutrinos, while potentially explaining why the universe contains more matter than antimatter, despite theoretical expectations for equal amounts. The neutrino mass hierarchy remains an unsolved problem in particle physics, with experiments unable to determine whether electron neutrinos are lighter or heavier than muon and tau neutrinos. This mass ordering affects neutrino oscillation probabilities and influences cosmic structure formation through neutrino contributions to dark matter density, making the hierarchy determination crucial for understanding both particle physics and cosmology. Geoneutrinos produced by radioactive decay of uranium, thorium, and potassium within Earth's interior provide information about the planet's composition and heat generation mechanisms that drive plate tectonics and magnetic field generation. These neutrinos carry direct information about radioactive elements deep within Earth's mantle and core, regions that remain inaccessible to direct sampling, but contribute significantly to planetary heat flow and geological processes. Supernova neutrino bursts could provide early warning systems for stellar explosions, with neutrinos arriving hours before visible light due to their ability to escape immediately from collapsing stellar cores, while photons remain trapped in dense stellar material. A network of neutrino detectors worldwide monitors continuously for sudden increases in neutrino flux that would signal nearby supernova explosions, potentially providing advance notice of spectacular astronomical events before they become visible to optical telescopes. The cosmic neutrino flux creates an invisible information network connecting every location in the universe to every other location through weakly interacting particles that preserve details about their sources across cosmic distances and timescales, carrying messages from stellar cores, supernova explosions, cosmic ray interactions, and the primordial universe itself in a constant stream of nearly massless messengers that pass through all matter essentially unnoticed, yet provide unique insights into cosmic phenomena invisible to all other forms of observation. The cosmic web forms an invisible scaffolding throughout the universe, constructed from dark matter filaments that span hundreds of millions of light-years, while connecting massive node concentrations where thousands of galaxies cluster together under gravitational attraction. This hidden architecture emerged from quantum fluctuations during cosmic inflation, when tiny density variations expanded to astronomical scales and provided gravitational seeds that grew through billions of years of cosmic evolution. Ordinary matter follows pathways carved by dark matter gravity, creating luminous galaxy distributions that trace underlying invisible structures like decorations strung along vast cosmic highways. Computer simulations reveal the cosmic web's intricate structure by modeling gravitational interactions among billions of dark matter particles over cosmic timescales, spanning from shortly after the Big Bang to the present day. These n-body calculations reproduce observed galaxy distributions with remarkable accuracy, when they include dark matter halos that outweigh visible matter by ratios exceeding 5:1. The largest simulations track dark matter evolution across volumes containing millions of galaxies, revealing hierarchical structure formation where small dark matter concentrations merge repeatedly to build progressively larger cosmic edifices. Galaxy surveys map the cosmic web's visible components by measuring distances to millions of galaxies across vast regions of space, revealing filamentary structures that connect dense cluster nodes through less dense void regions where galaxies remain sparse. The Sloan Digital Sky Survey and similar projects create three-dimensional maps showing how galaxies distribute along invisible dark matter filaments, with galaxy formation occurring preferentially where dark matter densities exceed critical thresholds for gravitational collapse and gas cooling. Voids occupy most of the universe's volume despite containing relatively few galaxies, creating vast underdense regions where dark matter filaments remain thin and widely separated. These cosmic voids span diameters exceeding 100 million light-years, while containing galaxy densities far below cosmic averages, demonstrating how gravitational instability creates extreme contrasts between overdense filaments and underdense void interiors. Only took 10 billion years for gravity to organize matter into the most empty and most crowded places imaginable. Apparently, the Lyman Alpha forest provides observational evidence for cosmic web structure through absorption lines in light from distant quasars, revealing how intergalactic gas distributes along dark matter filaments at high redshifts when the universe was younger and denser. These absorption features trace hydrogen gas clouds that remain too diffuse and cool to form stars, yet dense enough to absorb specific wavelengths of quasar light during its journey across cosmic distances. The forest pattern encodes information about dark matter distribution during epochs when cosmic structure was less evolved than today. Warm-hot intergalactic medium fills the space between galaxies with tenuous gas heated to temperatures exceeding 1 million degrees through gravitational collapse and shockwave heating as matter falls into dark matter potential wells. This hot gas contains approximately half of ordinary matter in the present-day universe, yet remains difficult to detect due to its low density and high temperature that places its emission lines in ultraviolet and X-ray wavelengths, requiring space-based observations to study effectively. Scientists wonder whether cosmic web structure reflects fundamental properties of dark matter beyond simple gravitational interactions, potentially requiring additional physics to explain observed galaxy distributions and void characteristics. Cold dark matter simulations predict more small-scale structure than observations detect, suggesting that dark matter properties might be more complex than initially assumed, or that baryonic physics plays larger roles in suppressing galaxy formation in low-mass dark matter halos. The Great Attractor represents a massive overdensity in the cosmic web that influences galaxy motions across hundreds of millions of light-years, creating bulk flows of galaxies toward this concentration despite cosmic expansion. This gravitational anomaly demonstrates how cosmic web inhomogeneities affect local galaxy dynamics. With the Milky Way and neighboring galaxies participating in large-scale motions driven by dark matter concentrations that remain largely invisible to electromagnetic observations, but reveal themselves through their gravitational influence on surrounding matter. Cosmic web evolution depends critically on dark energy's influence on cosmic expansion, with accelerating expansion working against gravitational collapse to halt structure formation on the largest scales. Future cosmic web development will be dominated by dark energy rather than gravitational attraction, leading to increasingly sparse galaxy distributions as cosmic expansion overwhelms gravity's ability to draw matter together into denser concentrations along filamentary pathways. Baryon acoustic oscillations preserved in galaxy clustering patterns reflect sound waves that propagated through the hot plasma-filling space before atoms formed and photons began traveling freely through the universe. These acoustic features provide standard rulers for measuring cosmic distances and expansion history, revealing how dark energy has influenced cosmic web growth rates throughout cosmic history. The oscillation wavelength depends on physical conditions during the universe's first 380,000 years, creating features in galaxy clustering that probe cosmic parameters. Galaxy formation occurs preferentially at dark matter halo intersections where multiple filaments converge, providing enhanced gas supplies and gravitational potential wells capable of retaining hot gas against stellar feedback and supernova explosions. The most massive galaxies form at cosmic web nodes where dark matter concentrations reach their highest values, while smaller galaxies populate filament regions with lower dark matter densities and reduced gas accretion rates. Void galaxies exhibit unusual properties compared to galaxies in filaments and clusters, showing enhanced star formation rates and different morphological characteristics that reflect their isolated environments within cosmic underdensities. These void dwellers form in rare dark matter concentrations within otherwise empty regions, creating natural laboratories for studying galaxy evolution under conditions of extreme isolation from neighboring galaxies and reduced environmental influences. The cosmic web's topology exhibits universal statistical properties that remain similar across different cosmic epochs and simulation parameters, suggesting fundamental relationships between gravitational instability and large-scale structure formation, filament connectivity, void size distributions, and node mass functions follow scaling laws that appear independent of detailed dark matter properties, indicating that cosmic web architecture reflects universal aspects of gravitational dynamics in an expanding universe. Future surveys will map cosmic web structure to unprecedented distances and detail using next-generation telescopes and gravitational lensing techniques that reveal dark matter distributions directly through their effects on background galaxy images. The Large Synoptic Survey Telescope and Euclid mission will measure weak gravitational lensing across billions of galaxies, creating detailed maps of dark matter filaments and void structures that trace cosmic web evolution from early times to the present day. Environmental effects within the cosmic web influence galaxy properties through processes like ram pressure stripping, tidal interactions, and strangulation that operate when galaxies move through dense intracluster gas or experience close encounters with neighboring galaxies along filamentary structures. These environmental mechanisms help explain observed correlations between galaxy properties and their locations within the cosmic web. From massive elliptical galaxies in cluster cores to star-forming spiral galaxies along filament peripheries, the cosmic web represents the largest scale organized structure in the universe. Emerging from quantum fluctuations during cosmic inflation and shaped by dark matter gravity into an invisible architecture that determined where galaxies form, how they evolve, and ultimately the distribution of all ordinary matter throughout space in patterns that span scales from individual galaxy halos to the observable universe itself, creating a hidden framework that connects every visible structure to the underlying dark matter foundation upon which cosmic evolution unfolds. Magnetic fields thread through galaxies in complex patterns invisible to human sight, extending across tens of thousands of light-years while influencing star formation, cosmic ray propagation, and the dynamics of interstellar gas throughout galactic disks and halos. These fields emerge from dynamo processes operating within rotating galaxies, where differential rotation and turbulent gas motions amplify weak seed magnetic fields over cosmic timescales spanning billions of years. The Milky Way's magnetic field strength reaches several microgauss throughout the galactic disk, comparable to Earth's magnetic field but extending across vastly larger volumes that encompass hundreds of billions of stars and their planetary systems. Spiral galaxies exhibit magnetic field patterns that often follow their optical spiral arms, creating invisible magnetic highways along which charged particles travel while being deflected away from regions where magnetic pressure opposes gravitational collapse. Radio telescopes reveal these magnetic structures through synchrotron emission, produced when cosmic ray electrons spiral through galactic magnetic fields at relativistic speeds, creating polarized radio waves that map field directions and strengths across galactic faces. The magnetic field patterns appear remarkably organized despite the chaotic processes that generate them through stellar feedback, supernova explosions, and turbulent gas dynamics. Galactic dynamos operate through the interaction between differential rotation and helical turbulence within galactic disks, gradually converting kinetic energy from gas motions into magnetic field energy through processes analogous to terrestrial dynamos, but operating on scales that dwarf planetary magnetic phenomena. The alpha-omega dynamo mechanism relies on rotation to stretch magnetic field lines azimuthally, while helical motions twist field lines to create poloidal components, establishing self-sustaining magnetic field configurations that can persist throughout galactic lifetimes, despite ohmic dissipation that would otherwise decay magnetic fields rapidly. Supernova explosions create expanding shock waves that compress and amplify magnetic fields while accelerating charged particles to cosmic ray energies, contributing to galactic magnetic field strength and cosmic ray populations that permeate interstellar space. These stellar explosions inject enormous amounts of energy into the interstellar medium, driving turbulent motions that help sustain galactic dynamo processes while creating magnetic field irregularities and local enhancements. Only took billions of supernovae to magnetize an entire galaxy. Apparently, scientists wonder whether primordial magnetic fields existed before the first stars formed, potentially providing seed fields for galactic dynamo amplification or influencing early star formation through magnetic pressure effects on collapsing gas clouds. Some theoretical models suggest that magnetic fields might have emerged during cosmic inflation, phase transitions in the early universe, or through battery mechanisms operating during cosmic recombination, when electrons and protons first combine to form neutral hydrogen atoms. Intergalactic magnetic fields exist in the vast spaces between galaxies, though their origins and properties remain largely mysterious due to the extreme difficulty of detecting such weak fields across cosmic distances. These fields might result from galactic winds that carry magnetized plasma into intergalactic space, primordial magnetogenesis during early cosmic epochs, or magnetic field generation through structure formation processes that operate during galaxy and cluster assembly. Gamma-ray observations of distant blazars provide indirect evidence for intergalactic magnetic fields through their effects on high-energy photon propagation. Magnetic reconnection events in galactic environments can suddenly release enormous amounts of stored magnetic energy, potentially triggering star formation episodes or launching galactic winds that eject gas from galactic gravitational wells. These reconnection processes occur when oppositely directed magnetic field lines encounter each other and reconfigure into lower energy states, converting magnetic energy into kinetic energy of charged particles and thermal energy of heated plasma in events that can affect galactic evolution over cosmic timescales. The Parker instability affects galactic magnetic fields by creating buoyant magnetic flux tubes that rise through galactic disks under the influence of cosmic ray pressure and magnetic buoyancy forces. This instability helps regulate star formation rates by removing gas from dense regions where stars would otherwise form rapidly, while also contributing to the escape of cosmic rays from galactic confinement and the injection of magnetized plasma into galactic halos and intergalactic space. Active galactic nuclei generate some of the most powerful magnetic phenomena in the universe, creating highly collimated jets of magnetized plasma that extend millions of light years from supermassive black holes at galactic centers. These jets require extremely strong magnetic fields near black hole event horizons to extract rotational energy from spinning black holes and focus plasma outflows into narrow beams that remain collimated across cosmic distances. The magnetic field configurations near black holes likely involve complex interactions between accretion disk dynamics and black hole spin. Magnetorotational instability drives turbulence in accretion disks around black holes and protostars, enabling angular momentum transport that allows matter to spiral inward, while magnetic stress transports angular momentum outward. This instability requires weak magnetic fields threading through rotating gaseous disks, demonstrating how magnetic fields can fundamentally alter gas dynamics, even when their energy density remains much smaller than gravitational or thermal energy densities. Cosmic ray confinement depends critically on galactic magnetic field configurations, with charged particles following magnetic field lines while experiencing occasional scattering from magnetic irregularities that trap cosmic rays within galactic volumes for millions of years before they escape into intergalactic space. The observed cosmic ray spectrum and composition reflect this magnetic confinement, with different particle energies experiencing different escape probabilities that depend on magnetic field strength and turbulence characteristics. Faraday rotation measurements reveal magnetic field properties along lines of sight to distant radio sources, as polarized radio waves experience rotation of their polarization planes proportional to the integrated magnetic field strength and electron density along propagation paths. These observations provide three-dimensional information about magnetic field structures throughout galaxies and galaxy clusters, though interpreting Faraday rotation data requires careful modeling of electron distributions and magnetic field geometries. Star formation regulation involves magnetic fields that provide additional pressure support against gravitational collapse in molecular clouds, potentially determining the initial mass function of forming stars and the efficiency with which gas converts into stellar populations. Magnetic fields can also channel gas flows during star formation, creating preferred directions for stellar outflows and influencing the formation of binary and multiple star systems through magnetic braking and reconnection processes operating within collapsing protostellar cores. Magnetohydrodynamic waves propagate through magnetized galactic gas, carrying energy and momentum across large distances, while potentially heating the interstellar medium and driving galactic fountains that transport gas between galactic disks and halos. These waves couple magnetic field dynamics to gas motions, creating complex feedback loops between star formation, stellar feedback, magnetic field evolution, and large-scale gas circulation patterns that influence galactic evolution over cosmic time. Galaxy interactions and mergers can dramatically affect magnetic field configurations by stretching, compressing, and reconnecting field lines during gravitational encounters between galactic systems. These interactions might temporarily enhance magnetic field strength through compression, while potentially disrupting organized magnetic field patterns and triggering starburst episodes through magnetic pressure variations and enhanced turbulence in interacting galactic gas distributions. The cosmic magnetic field network spans scales from planetary magnetospheres to galaxy clusters and potentially beyond, creating an invisible infrastructure that influences charged particle motions throughout the universe, while remaining undetectable except through its effects on radio emission, cosmic ray propagation, and the polarization properties of electromagnetic radiation that carries information about magnetic field configurations across cosmic distances and timescales spanning from stellar formation epochs to the present-day universe. The quantum vacuum thrums with activity even at absolute zero temperature. Where classical physics predicts perfect stillness, But quantum mechanics demands constant fluctuations that cannot be eliminated by any cooling process. Zero-point energy represents the irreducible minimum energy that quantum fields possess in their ground states, arising from Heisenberg uncertainty relations that prevent simultaneous precise knowledge of field values and their rates of change at any location in space. These quantum fluctuations create virtual particle pairs that spontaneously appear and disappear throughout empty space, briefly borrowing energy from the vacuum before annihilating back into nothingness, within time frames so short that energy conservation cannot detect their presence. Every quantum field contributes zero-point energy to the vacuum state, with electromagnetic fields alone providing energy density that theoretical calculations suggest should be enormous compared to observed cosmic energy densities. The sum over all possible photon modes yields infinite energy density unless physicists impose artificial cutoffs at high frequencies. Yet even modest cutoffs produce vacuum energy densities that would cause space itself to collapse immediately under gravitational forces. This cosmological constant problem represents one of theoretical physics' most severe fine-tuning issues, requiring vacuum energy to be either exactly zero or carefully balanced by unknown mechanisms. Experimental evidence for zero-point energy emerges through the Casimir effect, where two parallel metal plates placed extremely close together in perfect vacuum experience attractive forces generated by quantum field fluctuations in the narrow gap between them. The plates restrict which electromagnetic modes can exist in the confined space, creating lower energy density between the plates compared to the surrounding vacuum and producing measurable attractive forces. Only took 50 years after theoretical prediction to measure forces generated by absolutely nothing. Apparently, the quantum vacuum state differs fundamentally from classical emptiness by maintaining correlations and entanglements between widely separated regions of space, creating non-local connections that transcend familiar notions of spatial separation. Vacuum fluctuations at different locations exhibit quantum correlations that cannot be explained by local realistic theories, suggesting that empty space itself possesses intrinsic quantum structure that remains hidden from direct observation, yet influences the behavior of matter and energy throughout the universe. Hawking radiation emerges from quantum vacuum fluctuations near black hole event horizons, where gravitational tidal forces separate virtual particle pairs before they can annihilate and allow one member of each pair to escape while the other falls into the black hole. This process gradually reduces black hole mass while creating thermal radiation, with temperatures inversely proportional to black hole masses, demonstrating how quantum vacuum properties can produce observable effects in strong gravitational fields that amplify normally undetectable quantum phenomena. Scientists wonder whether vacuum energy might explain dark energy's observed effects on cosmic expansion, though the magnitude discrepancy between theoretical predictions and observations exceeds 100 orders of magnitude. Alternative approaches suggest that vacuum energy might be screened by unknown mechanisms, or that space-time itself might possess properties that prevent vacuum fluctuations from gravitating in the same manner as ordinary matter and energy. The Unruh effect predicts that uniformly accelerated observers should detect thermal radiation from quantum vacuum fluctuations, experiencing what appears as a warm bath of particles despite starting from a vacuum state as measured by inertial observers. This effect demonstrates how the concept of vacuum depends on the observer's motion, with accelerated reference frames detecting particle content that remains invisible to non-accelerated observers. The Unruh temperature depends linearly on acceleration magnitude, creating connections between thermodynamics and space-time geometry. Vacuum birefringence represents a quantum electrodynamics prediction where strong magnetic fields alter the polarization properties of light, passing through apparently empty space by inducing virtual electron-positron pairs that interact with photons through quantum loop effects. These virtual particles create anisotropic vacuum properties that affect light propagation differently for different polarization directions, producing measurable effects in the vicinity of neutron stars and other objects with extreme magnetic field strengths. The dynamical Casimir effect occurs when boundary conditions change rapidly enough to excite real particles from quantum vacuum fluctuations, converting virtual particles into observable radiation through mechanical motion of reflecting surfaces or time-varying electromagnetic fields. These experiments demonstrate that vacuum fluctuations represent genuine physical phenomena rather than mere mathematical artifacts, with sufficient energy density to create detectable particle production when appropriate conditions disturb the vacuum state. Vacuum decay scenarios suggest that our observed vacuum state might be metastable, rather than representing the lowest possible energy configuration, with quantum tunneling potentially triggering transitions to true vacuum states with different physical laws and particle properties. Such vacuum decay would propagate as an expanding bubble traveling at light speed, fundamentally altering physics within the affected region, and potentially destroying all existing structures by changing particle masses and force strengths. The quantum vacuum exhibits memory effect where previous disturbances leave persistent modifications to vacuum state properties, creating correlations between events separated in time through vacuum-mediated interactions. These memory effects operate through quantum coherence preservation in vacuum fluctuations, demonstrating that empty space can store and transmit information across arbitrary time intervals, despite containing no observable matter or energy. Vacuum polarization occurs when external electric fields modify quantum vacuum properties by biasing virtual particle pair creation toward configurations that screen applied fields, effectively giving the vacuum dielectric properties similar to polarizable materials. Strong electric fields near charged particles create vacuum polarization effects that contribute to measured particle properties and interaction strengths, requiring quantum electrodynamics calculations to achieve theoretical precision matching experimental observations. Zero-point motion affects all quantum systems, preventing atoms from collapsing despite electromagnetic attractive forces and maintaining molecular vibrations that persist even at absolute zero temperature. This quantum mechanical requirement ensures that matter retains finite size and exhibits thermal properties that remain non-zero, regardless of cooling efficiency, demonstrating how vacuum fluctuations influence macroscopic material properties through collective quantum effects. Squeezed vacuum states represent quantum field configurations where fluctuations are reduced below 0-point levels in some observables while necessarily increased in complementary observables to satisfy uncertainty relations. These non-classical vacuum states enable enhanced precision measurements and quantum-enhanced sensing applications, though their preparation requires sophisticated quantum control techniques and isolation from environmental decoherent sources. The cosmological constant represents vacuum energy's contribution to Einstein's field equations, affecting cosmic expansion rates and the formation of large-scale structure throughout cosmic history. Observations suggest that vacuum energy density, if it exists, must be extraordinarily small compared to theoretical expectations, requiring either precise cancellations between different contributions or fundamental modifications to how vacuum energy couples to gravity. Vacuum entanglement connects quantum field fluctuations across arbitrary spatial separations, creating correlation patterns that extend throughout the observable universe and potentially influence the emergence of classical spacetime geometry from quantum mechanical foundations. These vacuum correlations might play essential roles in black hole information paradox resolution, and the holographic principle relating bulk spacetime physics to boundary quantum information. The quantum vacuum represents the foundational level of reality from which all observable phenomena emerge through excitations, interactions, and symmetry-breaking mechanisms that operate continuously throughout space and time, creating an invisible substrate of zero-point energy and quantum correlations that underlies every physical process, while remaining forever hidden from direct observation, except through its subtle influences on matter, energy, and space-time geometry that pervade the universe at all scales from subatomic to cosmic. Gravitational waves propagate through space-time itself as ripples in the fundamental fabric of reality, carrying information about cosmic events across billions of light-years without absorption, scattering, or modification by intervening matter or electromagnetic fields. These disturbances represent oscillations in spacetime geometry that stretch and compress distances in perpendicular directions as they pass, creating measurable effects on the relative positions of test masses separated by kilometers, despite amplitude changes smaller than 1/10,000th the width of a proton. Einstein's general relativity predicted these waves a century before technology developed sufficient precision to detect them, demonstrating how mathematical theory can reveal hidden aspects of reality decades before experimental confirmation becomes possible. The first direct detection of gravitational waves occurred in September 2015 when the Laser Interferometer, Gravitational Wave Observatory, measured spacetime distortions caused by two black holes spiraling together and merging approximately 1.3 billion light-years from Earth. This collision released more energy in gravitational waves during its final fraction of a second than all visible stars in the observable universe emit as electromagnetic radiation, creating spacetime vibrations that traveled across cosmic distances to reach Earth with clockwork precision matching theoretical predictions. Only took 100 years and the most sensitive measuring devices ever constructed to hear spacetime itself vibrating. Apparently, gravitational wave astronomy opens observational windows into cosmic phenomena that remain completely invisible to electromagnetic telescopes, revealing the dark universe of black hole mergers, neutron-star collisions, and potentially primordial gravitational waves from cosmic inflation itself. These spacetime ripples carry information about mass distributions, spin orientations, and orbital dynamics during the final moments before compact object coalescence, providing direct measurements of strong field gravity regimes where spacetime curvature reaches extreme values impossible to reproduce in terrestrial laboratories. The generation of gravitational waves requires accelerating masses arranged in non-spherically symmetric configurations, with the strongest sources involving compact objects orbiting each other at significant fractions of light speed before merging catastrophically. Binary black holes lose orbital energy through gravitational wave emission that causes their orbits to decay gradually over millions of years before accelerating rapidly during final in-spiral phases lasting only minutes. The gravitational wave frequency increases continuously as orbital separation decreases, creating characteristic chirp signals that encode information about component masses and spins. Neutron star mergers produce gravitational wave signals accompanied by electromagnetic counterparts across the entire spectrum from radio waves to gamma rays, creating multi-messenger astronomy opportunities where gravitational and electromagnetic observations provide complementary information about the same cosmic events. The detection of gravitational waves from colliding neutron stars confirmed theoretical predictions about heavy element nucleosynthesis, revealing that these mergers create substantial fractions of gold, platinum, and other elements heavier than iron through rapid neutron capture processes operating under extreme conditions. Scientists wonder whether primordial gravitational waves from cosmic inflation might be detectable as polarization patterns in the cosmic microwave background radiation, potentially providing observational evidence for inflation theory and insights into physics at energy scales approaching the Planck regime. These primordial waves would have wavelengths comparable to the observable universe today, having been stretched by cosmic expansion from quantum fluctuations during inflation to macroscopic scales that affect microwave background polarization through their interactions with matter and radiation during cosmic recombination. The strain sensitivity of gravitational wave detectors must reach extraordinary levels to measure space-time distortions from astrophysical sources, requiring laser interferometers with arm lengths of several kilometers and displacement sensitivities approaching the fundamental quantum limits imposed by photon shot noise and radiation pressure fluctuations. Advanced LIGO achieves strain sensitivities better than 10^23 across frequency ranges from tens to thousands of hertz, enabling detection of black hole and neutron star mergers throughout volumes encompassing billions of galaxies. Gravitational wave propagation differs fundamentally from electromagnetic wave propagation by traveling through space-time rather than through space, making these disturbances unaffected by matter distributions along their propagation paths, while preserving source information with extraordinary fidelity across cosmic distances, unlike electromagnetic radiation that can be absorbed, scattered, or modified by intervening gas, dust, or magnetic fields. Gravitational waves pass through all matter virtually unimpeded, while carrying pristine information about their sources encoded in amplitude, frequency, and polarization patterns. The memory effect in gravitational waves creates permanent space-time distortions that persist after wave trains pass, leaving test masses in slightly different relative positions compared to their initial configurations. This effect arises from nonlinear aspects of general relativity, where gravitational waves interact with their own space-time curvature, creating lasting changes in local geometry that accumulate over time during extended gravitational wave emission episodes from insprawling compact object binaries. Pulsar timing arrays use millisecond pulses as cosmic clocks to search for gravitational waves with periods ranging from months to decades, potentially detecting supermassive black hole binaries in distant galactic centers that emit low-frequency gravitational radiation below the sensitivity range of ground-based interferometers. These natural timing arrays monitor pulse arrival times from dozens of pulses scattered throughout the galaxy, searching for correlated timing residuals that would indicate gravitational wave-induced spacetime distortions affecting light travel times from different pulsars. Space-based gravitational wave observatories like the planned Laser Interferometer Space Antenna will detect gravitational waves at frequencies inaccessible to ground-based detectors, using spacecraft separations of millions of kilometers to achieve sensitivity to massive black hole mergers throughout cosmic history and white dwarf binaries within our own galaxy. These space missions will probe gravitational wave sources across frequency ranges spanning several orders of magnitude, revealing cosmic phenomena invisible to both electromagnetic telescopes and ground-based gravitational wave detectors. The polarization properties of gravitational waves encode information about source orientations relative to Earth, and provide tests of general relativity's predictions about gravitational radiation characteristics compared to alternative theories of gravity. General relativity predicts that gravitational waves possess two independent polarization states, corresponding to quadrupolar spacetime distortions, while some alternative theories predict additional polarization modes that would create distinctive signatures in detector networks sensitive to multiple polarization components. Gravitational wave background radiation might exist as a stochastic combination of unresolved sources throughout cosmic history, creating random space-time fluctuations detectable through cross-correlation analysis between multiple gravitational wave detectors operating simultaneously. This background could include contributions from primordial gravitational waves, phase transitions in the early universe, cosmic string networks, or the superposition of countless unresolved black hole and neutron star mergers throughout cosmic time. The detection of gravitational waves confirms Einstein's general relativity in strong field regimes where space-time curvature approaches its most extreme values, validating theoretical predictions about black hole properties, neutron star equations of state, and the fundamental nature of gravity itself. These observations provide precision tests of general relativity under conditions impossible to reproduce artificially, demonstrating that Einstein's century-old theory accurately describes gravitational phenomena across scales from laboratory experiments to cosmic catastrophes. Continuous gravitational wave emission from rapidly rotating neutron stars with surface irregularities would create nearly monochromatic signals detectable through long-term coherent analysis of interferometer data, potentially revealing information about neutron star interior physics and the exotic matter states that exist at nuclear densities exceeding atomic nuclei. These searches require computational techniques capable of tracking potential signals over observation periods spanning months or years, despite Doppler shifts caused by Earth's orbital motion. Future gravitational wave observations will probe cosmic history back to the universe's first moments when primordial black holes might have formed, phase transitions might have occurred, and inflation might have generated detectable gravitational wave backgrounds that preserve information about physics operating at energy scales far beyond the reach of terrestrial particle accelerators, making gravitational wave astronomy a unique window into fundamental physics and cosmic evolution, spanning from quantum gravity regimes to the large-scale structure of space-time itself. Quantum particles exist in multiple states simultaneously until observation forces them to collapse into single realities, creating superposition configurations where electrons orbit atoms in all possible energy levels at once. Photons travel through multiple paths simultaneously, and particles possess definite properties only when measurement devices probe their quantum states. This fundamental aspect of quantum mechanics challenges classical intuitions about reality by requiring particles to exist in probabilistic combinations of all possible states, rather than possessing definite properties independent of observation. The mathematics of quantum mechanics describes these superposition states through wave functions that encode probability amplitudes for all possible measurement outcomes, with the squared amplitudes determining the likelihood of observing specific results. Schrödinger's cat illustrates the conceptual difficulties that quantum superposition creates for understanding macroscopic reality, where a hypothetical cat remains simultaneously alive and dead until observation determines its actual state through interaction with quantum measurement apparatus. This thought experiment highlights the measurement problem in quantum mechanics, questioning how and when quantum superposition transitions to classical definiteness during the measurement process. The cat exists in superposition only as long as quantum coherence persists between different possible states, with environmental decoherence eventually destroying superposition through uncontrolled interactions with surrounding matter. The double-slit experiment demonstrates superposition by showing how individual particles create interference patterns characteristic of wave-like behavior when passing through multiple apertures simultaneously, yet produce particle-like detection events at specific locations on observation screens. Each particle appears to travel through both slits at once, interfering with itself to create regions of constructive and destructive interference that build up statistical patterns over many individual detection events. Only took a century to realize that particles somehow know about paths they didn't take. Apparently, quantum computers exploit superposition to perform calculations using quantum bits that exist in probabilistic combinations of 0 and 1 states simultaneously, potentially enabling exponential speed-ups for specific computational problems compared to classical computers that process information using definite binary digits. Quantum algorithms manipulate superposition states through controlled interactions that create interference patterns, amplifying correct answers while cancelling incorrect solutions. Though maintaining quantum coherence during computation requires careful isolation from environmental decoherence that destroys superposition, scientists wonder whether consciousness plays essential roles in quantum measurement, or whether decoherence through environmental interactions provides sufficient explanation for the apparent collapse of superposition states into definite classical outcomes. Some interpretations suggest that conscious observation fundamentally alters physical reality by selecting specific outcomes from quantum superposition, while others propose that decoherence creates apparent wave function collapse without requiring conscious observers or fundamental changes to quantum state evolution. Many worlds interpretation suggests that all possible measurement outcomes occur simultaneously in parallel realities, with apparent wave function collapse resulting from observers becoming entangled with quantum systems and experiencing only one branch of constantly branching universal wave function evolution. Under this view, Schrödinger's cat remains both alive and dead in different universal branches, with conscious observers existing in multiple versions that each experience definite measurement outcomes while remaining unaware of parallel realities where different outcomes occurred. Decoherence theory explains how quantum superposition appears to collapse through interactions with environmental degrees of freedom that cannot be controlled or monitored precisely, creating apparent classical behavior from underlying quantum evolution without requiring fundamental modifications to quantum mechanics. Large systems maintain superposition for extremely brief periods due to their unavoidable interactions with surrounding matter, electromagnetic fields, and gravitational effects that entangle quantum states with environmental systems containing enormous numbers of unobservable degrees of freedom. The quantum Zeno effect demonstrates how frequent measurements can freeze quantum evolution by repeatedly collapsing wave functions before significant changes occur between observations, effectively preventing quantum systems from evolving through superposition states toward different measurement outcomes. This effect shows that the act of measurement itself influences quantum dynamics, with observation frequency determining how rapidly quantum systems can transition between different possible states during their evolution. Macroscopic quantum superposition has been demonstrated in specialized systems like superconducting quantum interference devices, where electrical currents flow simultaneously in opposite directions around superconducting loops, creating observable superposition states involving billions of electrons moving coherently in multiple directions at once. These macroscopic quantum effects bridge the gap between microscopic quantum phenomena and classical physics, by demonstrating that quantum superposition can persist in systems large enough to observe directly. The measurement problem remains unresolved in quantum mechanics, with various interpretations proposing different mechanisms for the apparent transition from quantum superposition to classical definiteness during observation processes. Some approaches invoke conscious observers, others rely on environmental decoherence, and still others suggest that superposition never actually collapses, but only appears to collapse from limited observational perspectives within larger quantum systems. Quantum tunneling represents superposition in action, allowing particles to exist simultaneously on both sides of energy barriers while maintaining probability amplitudes for transmission through classically forbidden regions. This phenomenon enables radioactive decay, stellar nuclear fusion, and semiconductor device operation by permitting particles to access energetically inaccessible regions through quantum mechanical probability distributions that extend beyond classical turning points. Coherent superposition states can be prepared artificially in laboratory systems using laser pulses, magnetic fields, and other controlled perturbations that create specific combinations of quantum states with definite phase relationships. These engineered superposition states enable precision measurements, quantum sensing applications, and fundamental tests of quantum mechanics under controlled conditions, where environmental decoherence can be minimized through careful experimental design. The correspondence principle suggests that quantum superposition should become negligible for large classical systems, with quantum effects averaging out to produce classical behavior when action scales become large compared to Planck's constant. However, the precise boundary between quantum and classical regimes remains unclear, with ongoing research investigating how large quantum systems can maintain superposition and whether fundamental limits exist for macroscopic quantum coherence. Quantum field theory extends superposition to field configurations, where particles represent excitations of underlying fields that exist in superposition states involving different numbers of particles at various locations throughout space. Virtual particles emerge from field superposition states, where vacuum fluctuations create temporary particle-antiparticle pairs that exist briefly before annihilating back into vacuum, demonstrating how superposition operates at the most fundamental level of physical reality. The quantum measurement process itself involves interactions between quantum systems and measurement apparatus that create entanglement between measured systems and detector states, potentially explaining apparent wave function collapse through the spreading of quantum correlations across increasingly large numbers of environmental degrees of freedom, until classical behavior emerges from quantum foundations. Superposition underlies all quantum phenomena from atomic energy levels to laser operation, chemical bonding, and biological processes like photosynthesis that might exploit quantum coherence to achieve remarkable efficiency in energy transfer through organic molecular complexes. These applications demonstrate that superposition represents not just an abstract theoretical concept, but a fundamental aspect of reality that enables the complex behaviors of matter and energy throughout the universe. The persistence of quantum superposition depends critically on isolation from environmental perturbations that entangle quantum systems with external degrees of freedom, creating apparent decoherence that transforms pure quantum states into statistical mixtures resembling classical probability distributions while preserving underlying quantum mechanical evolution within larger combined systems that include both quantum systems and their environments. Quantum superposition suggests that reality possesses far richer structure than classical physics assumed, with definite properties emerging only through measurement interactions, while underlying quantum states maintain simultaneous existence in multiple configurations that remain hidden from direct observation, yet influence all physical processes through interference effects and probability amplitude, evolution, that governs the statistical outcomes of experimental measurements performed throughout the quantum mechanical universe. Dark energy comprises approximately 70% of the universe's total energy density, yet its nature remains completely mysterious despite driving the accelerating expansion of space itself throughout cosmic history. This unknown force appears to possess negative pressure that creates repulsive gravitational effects, causing distant galaxies to recede from each other at ever-increasing rates, despite the attractive gravitational influence of matter that should slow cosmic expansion. Observations of distant supernovae revealed this cosmic acceleration in 1998, overturning expectations that universal expansion should decelerate under gravitational attraction, and introducing one of cosmology's most profound puzzles. The cosmological constant represents the simplest theoretical explanation for dark energy, suggesting that empty space itself possesses intrinsic energy density that remains constant as the universe expands. Einstein originally introduced this constant to permit static universe models, later calling it his greatest mistake when Hubble discovered cosmic expansion. However, quantum field theory predicts that vacuum energy should contribute enormous cosmological constant values that would prevent any cosmic structure formation, requiring extraordinary fine-tuning or unknown cancellation mechanisms to produce the small observed dark energy density. Dark energy's influence becomes dominant when cosmic expansion dilutes matter density sufficiently that dark energy's constant density begins to exceed the decreasing matter density throughout expanding space. This transition occurred approximately 5 billion years ago when the universe was roughly half its current age, marking the beginning of accelerated expansion that will continue indefinitely if dark energy properties remain constant. Only took 10 billion years for empty space to win the cosmic tug-of-war against gravity. Apparently, quintessence models propose that dark energy arises from slowly evolving scalar fields similar to the inflaton field that drove cosmic inflation during the universe's first moments, but with much smaller energy densities and slower evolution rates that permit cosmic structure formation while gradually accelerating expansion. These dynamic dark energy models allow for time-varying equation of state parameters that could potentially be distinguished from cosmological constant behavior through precision observations of cosmic expansion history. Scientists wonder whether dark energy represents a modification of general relativity on cosmic scales rather than a new form of energy filling space, motivating alternative theories where gravitational physics changes behavior at low curvatures or large distances. Modified gravity approaches attempt to explain cosmic acceleration without invoking mysterious energy components, though these theories must simultaneously explain dark energy effects while preserving general relativity's successes in describing solar system dynamics and gravitational wave observations. The cosmic coincidence problem questions why dark energy density and matter density became comparable during the epoch when intelligent life emerged to observe the universe. Despite their completely different evolution rates throughout cosmic history, matter density decreases as the inverse cube of cosmic scale factor, while dark energy density remains constant, making their current near equality appear surprisingly special unless anthropic selection effects or unknown physical mechanisms enforce this relationship. Type Ia supernovae serve as standard candles for measuring cosmic expansion history, because these stellar explosions reach similar peak luminosities, regardless of their host galaxy properties, enabling distance measurements to galaxies billions of light-years away. The observed dimming of distant supernovae compared to expectations from decelerating expansion models provided the first evidence for cosmic acceleration. revealing that space itself expands faster than gravitational attraction can slow the expansion rate. The equation of state parameter W characterizes dark energy through the ratio of pressure to energy density, with W discussed as 1 corresponding to cosmological constant behavior and other values indicating dynamic dark energy evolution. Current observations constrain W to remain close to 1 throughout recent cosmic history, though future surveys aim to detect potential time variations that would distinguish between different dark energy models and provide insights into fundamental physics operating on cosmic scales. Baryon acoustic oscillations in galaxy clustering provide complementary evidence for dark energy by measuring how cosmic expansion affects the characteristic scale of density, fluctuations frozen into matter distributions during cosmic recombination. These standard rulers enable geometric tests of cosmic expansion history independent of supernova observations, confirming accelerated expansion while constraining dark energy properties through precision measurements of angular diameter distance to different redshifts. The fate of the universe depends critically on dark energy's long-term behavior, with constant dark energy leading to exponential expansion that eventually separates all gravitationally unbound structures beyond observable horizons. If dark energy strengthens over time, phantom energy scenarios could lead to big rip outcomes where accelerating expansion eventually overcomes all attractive forces and tears apart atoms themselves. Alternatively, dark energy might weaken or reverse, potentially leading to eventual cosmic collapse in Big Crunch scenarios. Vacuum decay represents a speculative dark energy mechanism where the observed vacuum state exists in a metastable configuration that could transition to lower energy states through quantum tunneling, fundamentally altering physics throughout regions of space affected by vacuum phase transitions. These phase transitions would propagate at light speed while changing fundamental constants and particle properties, potentially destroying existing structures while creating regions with different physical laws. The holographic principle suggests deep connections between dark energy and quantum information theory, proposing that cosmic acceleration might reflect fundamental limits on information storage capacity within cosmic horizons. Some models suggest that dark energy emerges from entanglement entropy associated with cosmic horizon areas, creating connections between cosmic acceleration and quantum mechanical foundations of spacetime geometry. Dark energy surveys aim to constrain its properties through observations of billions of galaxies across cosmic history, measuring how dark energy affects structure formation, gravitational lensing, and cosmic expansion rates throughout different epochs. The Dark Energy Survey, Euclid Mission, and other projects will map dark energy's influence with unprecedented precision, potentially revealing whether it represents vacuum energy, evolving fields, or modifications to gravitational physics. The multiverse hypothesis suggests that our universe's dark energy density might be determined by anthropic selection from vast ensembles of universes with different vacuum energy values, with only universes having appropriate dark energy densities permitting galaxy formation and biological evolution. This approach addresses fine-tuning problems by invoking selection effects rather than fundamental physical mechanisms, though it remains highly speculative and difficult to test observationally. Interactions between dark energy and dark matter could potentially explain both phenomena through unified physical mechanisms, with some models proposing that dark energy and dark matter represent different aspects of single, underlying fields or modifications to gravitational physics. These unified dark sector models attempt to address multiple cosmic puzzles simultaneously, while reducing the number of unknown components required to explain observational cosmology. The observational evidence for dark energy comes primarily from geometric probes that measure cosmic expansion history and structure formation rates. With independent measurements from supernovae, cosmic microwave background anisotropies, baryon acoustic oscillations, and gravitational lensing all pointing toward cosmic acceleration driven by smooth energy components with negative pressure properties that distinguish dark energy from all known forms of matter. Future gravitational wave observations might provide new insights into dark energy through measurements of cosmological distances and expansion rates using standard sirens from binary compact object mergers, offering complementary approaches to optical astronomical techniques, while potentially revealing dark energy effects on gravitational wave propagation across cosmic distances spanning billions of years of cosmic evolution. Dark energy represents perhaps the greatest mystery in modern cosmology, comprising most of the universe's energy budget while remaining completely invisible except through its gravitational effects on cosmic expansion and structure formation, challenging theoretical physics to explain how empty space itself can possess properties that determine the ultimate fate of everything that exists within the expanding cosmos driven by this unknown force operating throughout space and time. At the smallest conceivable scales of reality, where distances approach the Planck length of 1035 meters and time intervals shrink to 1043 seconds. Space-time itself might dissolve into quantum foam, where the familiar concepts of distance, duration, and causality lose their classical meanings. These scales exist so far beyond direct observation that light wavelengths exceed the structures being probed by factors comparable to the ratio between atomic nuclei and galactic superclusters. Quantum gravity effects dominate at Planck scales, where virtual black holes might spontaneously appear and evaporate. Wormholes could connect distant regions of spacetime, and the smooth geometry of general relativity gives way to fluctuating topologies that create and destroy spatial connections faster than any measurement could detect. Virtual particle pairs emerge from quantum vacuum fluctuations at all scales, but near the Planck regime these virtual particles carry sufficient energy to create gravitational effects comparable to their electromagnetic and nuclear interactions. The uncertainty principle permits increasingly energetic virtual particles to exist for correspondingly brief intervals, with Planck scale fluctuations borrowing energy equivalent to particle accelerator collision energies, while existing for time periods billions of times shorter than the strong nuclear force interaction timescales. These extreme virtual particles might carry information between disconnected regions of spacetime through quantum tunneling effects that transcend classical notions of spatial separation. String theory suggests that fundamental particles represent vibrating strings or membranes operating at Planck scales, with different vibrational modes corresponding to different particle types and their characteristic masses, charges, and spins. These strings exist in 11-dimensional spacetime, where the extra dimensions curl into complex geometric configurations called Calabi-Yau manifolds that determine which particle types can exist and how they interact through fundamental forces. Only took decades of mathematical development to realize that reality might be music played on invisible strings. Apparently, loop quantum gravity proposes that spacetime itself possesses discrete structure at Planck scales, composed of quantized geometric building blocks that create apparent smoothness only when averaged over larger scales accessible to measurement. This approach suggests that space consists of interconnected loops and nodes, forming networks that evolve through discrete time steps, potentially resolving the singularities that plague general relativity by preventing infinite curvatures through fundamental granularity of spacetime geometry. Scientists wonder whether the Planck scale represents a fundamental boundary beyond which the concepts of space and time become meaningless, or whether even smaller scales exist with new physics operating according to principles that transcend current theoretical frameworks. Some approaches suggest that spacetime emerges from more fundamental quantum information structures, with geometric properties arising statistically from entanglement patterns between underlying degrees of freedom that exist independently of spatial and temporal concepts. The holographic principle operating at Planck scales might encode all information within any volume of space on its boundary surfaces, suggesting that three-dimensional physics emerges from two-dimensional quantum information processing occurring at horizon boundaries. This principle connects quantum gravity to information theory, while implying that spacetime dimensionality might represent an emergent property rather than a fundamental aspect of reality. With apparent three-dimensional space arising from holographic projections of boundary quantum computations, Planck-scale black holes, if they exist, would evaporate almost instantaneously through Hawking radiation, while potentially serving as elementary particles in theories where mass, charge, and spin emerge from black hole properties rather than fundamental particle characteristics. These microscopic black holes might mediate gravitational interactions between ordinary particles, creating discrete gravitational charge analogous to electric charge, but operating through quantum gravitational degrees of freedom invisible to classical general relativity. Causal dynamical triangulation attempts to construct spacetime from fundamental simplicial building blocks that evolve through Monte Carlo sampling of possible geometric configurations, seeking to understand how smooth spacetime emerges from discrete quantum geometric degrees of freedom. This approach reveals that appropriate classical spacetime dimensionality emerges naturally from quantum gravitational dynamics without requiring it to be imposed as a fundamental assumption, suggesting deep connections between geometry and quantum mechanics. The measurement problem becomes particularly acute at Planck scales, where quantum gravitational effects might fundamentally alter the relationship between observers and observed systems, potentially requiring new frameworks for understanding how classical measurement outcomes emerge from quantum gravitational foundations. Some approaches suggest that consciousness itself might represent quantum gravitational phenomena operating at Planck scales within neural microtubule structures, though such speculations remain highly controversial and lack experimental support. Emergent gravity theories propose that gravitational forces arise from more fundamental quantum mechanical phenomena operating at Planck scales, analogous to how thermodynamic properties emerge from statistical mechanics despite not existing at the level of individual particles. These approaches suggest that spacetime curvature represents collective behavior of underlying quantum degrees of freedom, rather than fundamental geometric properties, potentially explaining dark energy and dark matter through emergent gravitational phenomena. The cosmological constant problem becomes particularly severe when considered from Planck scale perspectives, where quantum gravitational effects should contribute enormous vacuum energy densities that would prevent any cosmic structure formation unless extraordinary cancellation mechanisms operate with precision exceeding 1 part in 10^120. This fine-tuning problem suggests either remarkable conspiracy in fundamental physics or missing theoretical understanding of how quantum gravity affects macroscopic spacetime properties. Planck-scale physics might preserve information that appears lost in black hole evaporation, with quantum gravitational effects encoding information about infalling matter in spacetime geometry, fluctuations too subtle to detect through classical measurements. The black hole information paradox might resolve through quantum gravitational mechanisms that preserve information unitarity while maintaining the thermal character of Hawking radiation through complementarity principles operating at horizon scales. Quantum tunneling events at Planck scales might create macroscopic effects through amplification mechanisms that stretch microscopic quantum gravitational fluctuations to astronomical scales, potentially explaining cosmic inflation, dark energy, or the origin of cosmic structure from primordial quantum gravitational seeds. These amplification processes would require carefully tuned initial conditions or dynamical mechanisms that naturally select appropriate fluctuation patterns for subsequent cosmic evolution. The arrow of time might emerge from quantum gravitational processes operating at Planck scales, where spontaneous symmetry breaking or decoherence mechanisms create preferred temporal directions through interactions between quantum gravity and matter fields. Some models suggest that time itself represents an emergent property arising from quantum gravitational entanglement patterns that create apparent temporal ordering from fundamentally timeless quantum mechanical foundations. Computational approaches to quantum gravity attempt to simulate Planck-scale physics using classical computers that model discrete space-time networks, quantum field interactions, and gravitational dynamics through numerical methods that approximate the behavior of inaccessible quantum gravitational regimes. These simulations provide insights into how macroscopic spacetime might emerge from microscopic quantum gravitational degrees of freedom, while testing theoretical predictions about Planck-scale physics. The relationship between quantum mechanics and general relativity at Planck scales remains one of theoretical physics' greatest unsolved problems, with various approaches proposing different mechanisms for unifying quantum field theory with gravitational physics. These attempts range from string theory and loop quantum gravity to emergent gravity and causal set theory, each offering different perspectives on how quantum gravitational phenomena might operate at the most fundamental scales. Future experimental tests of Planck-scale physics might emerge through precision measurements of gravitational wave propagation, cosmic microwave background polarization patterns, high-energy cosmic ray interactions, or laboratory tests of gravitational physics at short distances. Though directly probing Planck scales would require particle accelerators larger than galactic superclusters, operating at energies approaching those present during cosmic inflation itself, the Planck scale represents the ultimate frontier where human understanding approaches its most fundamental limits, revealing realms where space and time themselves might represent emergent approximations to deeper quantum gravitational realities that operate according to principles transcending classical physics, while determining every aspect of cosmic evolution from the first moments after the Big Bang through the formation of galaxies, stars, planets, and the emergence of consciousness capable of contemplating its own quantum gravitational foundations hidden within the invisible foam of spacetime itself. The dimensions that surround this moment stretch beyond perception, curling through spaces too small for light to illuminate, too brief for time to measure. Quantum fields hum their silent frequencies through every cubic centimeter of the room, every breath, every pause between heartbeats. Virtual particles dance their fleeting existence in the space between thoughts, borrowing energy from nothingness before returning to the vacuum that underlies all apparent stillness. Space-time curves gently around the mass of the body resting here, creating invisible valleys in the fabric of reality that guide photons from distant stars, neutrinos from the sun's core, cosmic rays from galactic centers billions of light-years away. The Higgs field maintains its constant presence, giving mass to every atom through interactions too fundamental to avoid, too essential to notice. Dark matter streams through this location in quantities that outweigh every visible object nearby, its gravitational influence shaping cosmic structures while remaining forever beyond direct touch. Magnetic field lines thread through this space, connecting solar activity to terrestrial aurora, galactic rotation to cosmic ray propagation, stellar birth to planetary formation across scales that dwarf imagination, yet operate within the volume of a single room. Gravitational waves from ancient black hole collisions pass through without resistance, carrying information about cosmic catastrophes that occurred when the universe was younger, smaller, more violent than the quiet cosmos visible tonight through bedroom windows. The electromagnetic spectrum extends far beyond visible wavelengths, bathing this moment in radio whispers from pulsars, infrared heat from cooling objects, ultraviolet echoes from stellar nurseries, gamma-ray signatures from matter falling into invisible black holes. Quantum entanglement connects particles here to partners scattered across arbitrary distances, maintaining correlations that transcend space while preserving the mystery of non-local reality operating beneath classical appearances. Consciousness settles into this intersection of invisible dimensions, resting among forces and fields that remain forever hidden yet determine every aspect of physical existence. The quantum vacuum fluctuates around sleeping thoughts. Dark energy accelerates cosmic expansion between dreams. Neutrinos stream through closed eyelids carrying messages from the universe's most energetic phenomena. All of this occurs in perfect silence, beyond sensation, within the invisible architecture that makes possible every visible thing. Time dilates slightly in Earth's gravitational field, flowing just a little faster for dreams than for the planet's core. The cosmic web extends its dark matter filaments through this bedroom, this building, this city, connecting local gravity to cosmic structure spanning billions of light years. Reality operates through dimensions curled too tightly to perceive, fields too weak to feel, scales too vast or too small for human senses to grasp. Sleep comes to consciousness embedded in invisible physics, cradled by forces that operate continuously without pause, surrounded by the hidden science of dimensions that remain forever beyond direct sight yet closer than breath, more intimate than thought, more fundamental than the boundary between sleeping and waking. Rest settles into the quantum foam from which space-time itself emerges, finding peace in the mystery of hidden realities that surround every moment with dimensions beyond counting, beyond seeing, beyond understanding, yet never beyond the quiet wonder of existing within their invisible embrace.